So the tiny machine is a perfectly typical von Neumann architecture. It's got a central processing unit with 4 registers in it. It's got a control unit, and it's got an arithmetic logic unit, which is a little piece of paper that I'll be able to do some calculations on. It's also got buses that connect to the main memory. And the main memory has a whole 16 locations, which means that to specify one of those locations, you have to specify 1 from 16 possibilities. That takes 4 bits, which we can easily represent as a hexadecimal number. And each memory location stores a 4-bit value. So the main memory of the tiny machine might well look like this. It's just 16 hexadecimal digits. That's 64 bits of memory, which these days is what one location of a modern computer would store. So we're working with a machine that's so tiny, its entire memory would fit in one memory location in a modern computer. But because it's so small, we'll be able to know it very well. Okay? What else does the tiny machine have? Well, it's a von Neumann architecture. So it has an input-output system. So it has, in this case, it has a queue of hexadecimal values waiting to be received through the input, and at the moment it has a currently empty queue of values that have been sent via the output. Okay, so I hope you have received one of these. A tiny machine reference guide. Anybody not got a tiny machine reference guide? Let's have another couple up this way. Any more? Yeah, well, you got one there. It's this piece of paper. It will either save your life or end it. The most important line on this piece of paper is the bottom one. It says, a copy of this document will be at your disposal in all relevant tests and examinations. That is to say, the information contained on this piece of paper need not be memorized. I do not expect you to remember all of these little details. That's why I always give you a copy of this piece of paper if there are any questions that are something to do with the tiny machine. I'm just happy to kill trees instead of burdening you with this much information. But then there's a lot of other chat here, which I don't expect you to understand yet, but which we'll need to acquire an understanding of. But let's find out how to be the tiny machine just by trying it. Okay, so let's start with the CPU. The way von Neumann machines work is that they repeatedly carry out a process called the fetch-execute cycle. And that means, remember, the program is stored in main memory. So in order to do a bit of work, the machine has to fetch a part of the program from main memory and then carry it out. And, yep?
Is it the exact same as the fetch-execute decode?
Yeah, and you'll see decoding is one of the steps.
Right.
So some people call it fetch, execute, decode. Some people, or fetch, decode, execute. Usually the words fetch and execute will be there, and possibly some other words, but that's the idea. So In the tiny machine, I'm going to need to find some pens. In the tiny machine, the fetch execute cycle starts by sending an instruction on the buses. Maybe I'll use a different color for that. We send an instruction on the buses. We need to fetch the first thing to do. So we're going to send a read memory request to the main memory. And we have to decide where we're going to read. The purpose of this register, the instruction pointer, is to say where in memory the next instruction is to be found. So the thing we send on the address bus for this memory read is exactly what the instruction pointer says. And that is currently 0. So we send a read 0 request on the buses. The CPU will send that request on the buses to the main memory. So here's our memory read request. And you can see it's referring to address 0. What's currently stored in address 0? E. Correspondingly, the E signal will be sent back on the data bus to the CPU. So the CPU has now acquired E. And we have completed phase 1 of the fetch execute cycle. That's called the operator fetch. And we've got E is the operator. The next step is indeed to decode the operator. For this, we require the tiny guide. We zoom in and we see that operator E is a thing called LDL, which is short for load loop index. So we've decoded the operator. The other thing we have to check is whether or not the instruction requires what's called an operand. So an operator is this thing. It's like a verb, what to do. And you know that some verbs make sense on their own, like, jump. And some verbs need a thing to be done to. So they need an object that the verb gets done to. And that's the same with the tiny machine. Some instructions just make sense on their own, and they fit into one location in memory. Others apply to an operand, and so the whole instruction takes up 2 locations in memory. So first of all, we look in the second column to see whether there's an operand or not. And when you see adder, which is short for address, in the operand column, that means the instruction does have an operand, and that operand will represent an address. If you just see a blank, that means the instruction does not have an operand. So the next step of the fetch execute cycle is called the operand fetch. When there is an operand, it is always stored in memory immediately after the operator. So the operand fetch will require us to send another read request on the buses. So we'll send a memory read request, and if the operator was in location 0, which is what the instruction pointer is telling us, that means the operand will be in the next location along. So we need to read what's in memory location number 1. So that's to say the control unit sends out a request on the buses to read memory location 1. Fine. Over in the memory, we receive the read request for location 1. What's going to happen? We'll look at what's in location 1, that's an F, and we send that value F back on the data bus to the CPU. So the CPU just got this F coming back on the data bus. Now we need to understand what to do. So, piece of notation for you. Let's just zoom in a bit. Let's learn what the effect of the instruction is. What is meant by this equation? Let's see. Well, the equal sign, the single equal sign, is an assignment. You've seen assignment in Python? Yeah, so it's saying the thing to the left of the equal sign is going to become the value to the right. The thing to the left of the equal sign is Li, that's the loop index register. So what's going to happen is that we're going to update the value of this register. What with? Well, we can see some square brackets round adder, and adder is a variable standing for the operand. So we just did an operand fetch, and we got F. So what this is really meaning is square brackets F in this, for this time round the cycle. Now what do the square brackets mean? The square brackets mean contents of. So we're not going to be updating Li, the loop index, with the value F. We're going to be treating F as the address from which we're going to load the new value of the loop index. So once again, we have to send a memory read request out on the buses. This time, we send a memory read request with that address, F. So, yeah, thanks. This is going to keep happening. Okay, so along the buses come the request to read memory location F. What happens? We send 3 back on the data bus. Okay? So now we have completed the operand fetch and everything that comes with it. Well, that was really part of execute instruction. We've obtained the 3 that was stored in memory location F, and now we have to finish the last stage of the cycle. Let me just give myself access to the registers. We have to update the registers in accordance with what just happened. There are, in this case, 3 things we need to do, for which I'll need some magic memory update juice. First of all, we actually have to perform the main part of the instruction, namely to load the loop index. We just received the value 3, so the 0 that was there before gets replaced by that 3. That's what the equation loop index equals contents of address means. It means see what's at that memory location, fetch it, put it in the loop index. There's another thing we have to do, which corresponds to this thing. Okay? This thing that says ZF equals the result of testing whether Li equals 0. So let's deal with the right-hand side first. Did we just make the loop index 0? No, we did not. So the result of this test will be false, otherwise known as 0. Now, anytime we do an operation which updates the loop index or the accumulator, we test if we just made it 0. And if we do, we set a signal to say that a 0 has been detected. And that signal is called the 0 flag. Where does the 0 flag live? It lives in the flag register. Oh, come on. I know, I felt that way this morning. The flag register contains 4 bits, which are separately the halt flag, the overflow flag, the 0 flag, and the carry flag. Those are the 8s, the 4s, the 2s, and the 1s of the flag register. And they all mean different things. So the flag register doesn't represent a number, it represents 4 separate bits. And the 0 flag is used to signal that a 0 has been detected. That's to say, the 0 flag becomes 1 when a 0 is detected. So you can see at the moment, the flag register, which we've zoomed in on conveniently, is 0. That means all 4 of its bits are 0. And we just did a test to detect a 0 in which no 0 was detected. So the effect of that update will be to keep the flag register at 0. Because nothing was detected. So we've checked, no 0 detected, 0 flag should be 0, and it is. That's fine. One last thing we need to do before we're ready to move on is to update the instruction pointer. And what we do is we add the size of the instruction that we just executed to the instruction pointer. So that instruction had an operator, load the loop index, and an operand, f, so it had size 2, which means we need to add 2 to the instruction pointer. So that moves on from 0 to 2. And that's ready for the next instruction. So we've made it through one cycle of the machine's execution. We fetched an operator, we saw it needed an operand, we decoded it, we saw it needed an operand, we fetched the operand, and then in order to do the instruction, we needed to do a further memory read, and then we updated the registers, loading the value into the loop index, checking for 0, and adding the size of the instruction to the instruction pointer. Okay, everybody, yep?
For working through an example, are we okay to assume that the operator will automatically increase the instruction pointer by 2 or 1 depending on whether it's needs an operand or not?
Well, since you will be the person who is being the instruction pointer, you will be responsible for making that update. So in particular, I happen to have here a very typical tiny tracing sheet. So with the current contents of memory in it. So if I was recording this trace, and this is the sort of thing I ask you to do, I would write LDL in the operator column, and I would write the operand that we read, which was the thing in location 1, that's an F, in the operand column. I would leave input and output blank, because no input or output happened using the input-output system. And then I would update the registers on the next line. So we just said instruction pointer goes up to 2, loop index becomes 3, and no change to the other 2 registers. So we're ready to go again. Maybe I won't labor the point of the, which bus communications happen, so we can go just a little bit faster. Okay. So, the instruction pointer is 2. That means we need to fetch the next instruction from memory. So, what gets sent back on the data bus? If we're fetching from, if the instruction pointer said 2, and we're doing the operator fetch, 6 comes back on the data bus. Okay. So now we need to decode 6. What is 6? 6 is get, which means get a new value for the accumulator from the input queue. So this funny little bit of notation here, left arrow question mark, means value coming from the input queue. And it's going into the accumulator. Okay. So we need to find the input-output system. Another bus interaction. On the control bus, there will be a command to get from the input queue. And we can see that there's currently, at the head of the input queue, there's this 6. So this 6 would be removed from the input queue, and it would arrive in the CPU. So we've done our, I should have checked, by the way. I should have checked, I'm going too fast. I should have just checked. You can see get does not have an operand. So there was no need to do an operand fetch. I should have put that step in. So check. No operand fetch. Get makes sense on its own. Yes?
It had an operand, get the value from address number 6?
No. It doesn't have an operand, so the hypothetical question doesn't apply. Get does not have an operand. It never has an operand. Yes. Some things have operands, but get does not. It always gets whatever's at the head of the input queue. So this value 6 that we received is the thing that's going to end up in the accumulator. That's what it's for, right? One of these things, there are rules for the tiny machine, and I made them up. You don't get to make up your own rules. The CPU follows the rules completely slavishly, and in this respect, you're going to get very, very bored. But you'll have an experience that's a lot like computation and hopefully learn from it. Hopefully it will stop being scary and start becoming very, very boring indeed. Right? One reason that we get computers to do this sort of stuff mechanically is just how boring it is. Okay, so we've got our value from the input queue. Now we have to carry on with the rest of the instruction. We've got to put it in the accumulator. So with a bit of rubbing out, I can write the 6 goes into the accumulator. What else do we have to do? We have to, because we just changed the accumulator, we have to do a 0 check. 6 is not 0. So we have not just detected a 0, so we can leave the flag register as it is. Yes?
Why is it important that there's not a 0?
Well, by the speed we're going, you'll see sometime next lecture. Right, so what's going to happen, we've just loaded the loop index, right? So the loop index register is used to make a countdown. We're going to, when we initialize the loop index with that value 3, that basically tells us, doesn't tell the computer, but it tells us, that we're going to go round a loop 3 times. We're going to count down the loop index until it reaches 0. And when it reaches 0, we're going to need to figure out that we ought to stop. And that's why detecting a 0 is important. Because quite often, it's the signal to change course. So in particular, things like The loop ends when the countdown reaches 0. It's an important bit of zero detection. Okay, so we did the 0 flag. One more thing we need to do.
Update the index pointer.
Update the instruction pointer. This time our instruction was only of size 1. There was no operand. So the instruction pointer only goes up by 1. It becomes 3. And in the immortal words of the average white band, let's go round again. Let's see. We've got to do an operator fetch. This time we're going to fetch from location 3. What's in location 3? F. All right. Let's decode F. F stands for flip accumulator. Does it have an operand? No. So there's no call to do an operand fetch. Let's see how to do the instruction. It says accumulator becomes F minus accumulator. So we're subtracting from F. Well, that's the same in 2's complement as subtracting from -1. That's to say, flip accumulator means flip all the bits of the accumulator. This looks like a job for the arithmetic logic unit. What do you get if you convert that value to binary? 4 bits of 0, 1, 1, 0.
Screen.
Yeah. Okay. So 6 in hex is 0, 1, 1, 0 in bin. In binary, we flip the bits, and we get 1, 0, 0, 1 in binary. What's that in hexadecimal? That's 9 in hexadecimal. So what I have to do, according to the instructions, is to update the accumulator to be 9 instead of 6. That's one of the things I have to do. Accumulator becomes 9. What else do I need to do? Check for 0. 9 is not 0. Thank goodness for that. And one more thing I need to do. One more thing I need to do is update the instruction pointer. What's the instruction pointer going to become? 4, because there was no operand. Now let's see what happens. Let's go round again. I think I'll do one more and then leave us with a cliffhanger. What's in memory location 4? Let's do the operator fetch. Zoom out. Yep. We got a C. Okay, let's do the decode. What does C mean? Set carry flag. Okay. So what I need to do, a bit more arithmetic logic unit. The flag register is currently 0. Oops. Yeah. What's 0 in 4-bit binary? Thank goodness for that. And that's halt flag, overflow flag, 0 flag, carry flag. Set carry flag means make the carry flag 1. So the other 3 all stay the same, but the carry flag becomes 1. Can you convert this to hexadecimal for me? It's a whole exciting one, isn't it? So that means the flag register becomes 1, and then we have to update the instruction pointer. What does it become? It becomes 5 because there was no operand. And let's get part of the way through this cycle before we stop. What is the, so we're, instruction pointer is 5. Can you do the operator fetch for me? That's A. Now can you do the operator decode for me? It's add with carry, and you can see that it's the biggest, ugliest, most complicated one. Which is why it's a very bad thing to rush at the end of a lecture. I'll give you a clue. Well, you can see it does have an operand. So, which memory location are we going to fetch the operand from? It's going to come from location 6, straight after the operator. So, what value will be fetched? E. And what does that represent? It represents an address. So we're not going to add E. We're going to add the value that is stored in memory location E. And that value is F. So let's just see what's happening. We got a value, we flipped its bits, and the instructions say, what do we add? The accumulator, the contents of the address, and the carry flag. We just set the carry flag to be 1. So we just got a value, we flipped its bits, we stuck an extra 1 in the carry flag, and now we're adding. What's going on? We've just basically made a negative number and we're adding it to something. We are subtracting. So we'll actually do the subtraction in the next lecture. We're going to be, we receive an input, we're going to subtract it from this value. Okay? So, can I have 1-minute papers in the boxes, please? You'll find, by the way, that there are 16 instructions in the tiny machine, 60 different operators, and last year, Stuart and I made a video for each single one of them. So on the tiny page, you can see a video for each operator explaining how to do it. And you're going to need to know how to do all of them.